How can the universe expand if it's already infinite? It sounds impossible, like asking a horizon to step farther away. If there's no edge to space, where is it going? And yet, that's what the evidence says. The distances between far-off galaxies are growing. No center, no blast wave, just more space between things. Tonight, we're going to make that feel simple. No math, no jargon, just clear pictures you can keep in your head long after the lights are out. We'll slow the pace, breathe a little, and let the idea unfold the way night does, quietly, steadily, one star at a time. Here's the promise. By the end of this, infinite won't feel like a brick wall, and expansion won't sound like a contradiction. You'll see how both can be true at once. We'll tidy up a few slippery words, build a mental model you can trust, and then gently layer on what astronomers actually see when they point big mirrors at the dark. No big reveals yet. Let the paradox hang in the air for a moment. Picture a sky that looks the same in every direction, and yet, over long stretches of time, the landmarks drift. Not because anyone's sailing toward an edge, there isn't one, but because the ocean itself is making more ocean. If that image creates a little spark behind your eyes, good. Hold it. Get comfortable. When you're ready, we'll take the first real step. What infinite means in cosmology, and why it doesn't behave the way our everyday words think it should. Let's start by sanding down the word that keeps tripping us. Infinite. In everyday talk, infinite can sound like everything, everywhere, all at once. In cosmology, it's simpler and less dramatic. It just means no edge. Picture a straight line in math class. It goes on forever in both directions. You never hit a wall, but at any given moment, you only stand in one spot. That's the flavor of infinity we're using, extent without a boundary, not a promise that every fantasy happens somewhere. Now, we also need to separate two ideas people often mash together: the whole universe and the observable universe. The observable part is just the region from which light has had time to reach us since the cosmic clock started. Light is fast, but the universe is old and big, and light needs time. So we live inside a kind of light bubble, our horizon. Beyond that horizon may lie more of the same, maybe endlessly more. Crucially, the horizon is not a wall out in space that you could visit. It's a limit in time and causality, the farthest distance that can have affected us so far. A small analogy. Imagine you're in a foggy field at night with a lantern. You can see a circle of grass around you. That circle is your observable field. Does the field stop where your light fades? No, your vision does. If you wait and the fog thins, you'll see farther. The land didn't grow. Your horizon expanded. With the universe, something similar though subtler happens as time passes. More light has time to arrive, so our horizon grows. But because space itself expands, some distant places are receding so fast that their light will never reach us. So the horizon is a living boundary, shaped by both time and expansion. Okay, back to infinite. Could the whole universe be infinite? Yes. Current measurements suggest that on the larger scales, space is very close to flat, not shaped like a giant sphere or a saddle. A perfectly flat geometry can be infinite in extent. Think of an endless chessboard, square after square with no edge. We only see a finite patch of it, our observable universe, but the pattern could continue without stopping. We don't know for sure, because we can't see past our horizon, but an infinite universe is consistent with what we observe. Here's another helpful split: unbounded versus infinite. A surface can be unbounded, no edges, without being infinite in area. The classic example is the surface of a sphere. Walk on Earth and you never meet an edge. You just keep looping. That surface is finite yet unbounded. Flat space can be unbounded and infinite. The point is, no edges doesn't automatically tell you whether the total size is finite or infinite. It tells you about boundaries. not about total area. Now bring the everyday brain back in. If something is already boundless, how can it get bigger? The key is that expansion isn't about creating new rooms on the far side of an edge. It's about changing the scale of distance between the points that already exist. Think of the numbers on a ruler printed on stretchy rubber. If you stretch the rubber, the marks move farther apart. The ruler has no end in the mathematical sense. It could have been imagined to go on forever, but the spacing between its marks can still increase. Infinity doesn't protect distances from changing. Another tripwire word is center. If there's expansion, where is it centered? Nowhere or everywhere. In an expanding universe that looks roughly the same in all directions and places, on average, every galaxy sees other faraway galaxies moving away. That's not because they're sprinting through space from a central explosion. It's because the fabric of space is increasing distances between them. Like dots on that stretchy rubber, each dot watches the others recede, and each dot can honestly claim, it looks like I'm at the center, without there being a true center. One last note before we move on. Infinity here doesn't mean infinite energy, or infinite brightness, or any of the troubling infinities you might have heard in other contexts. We're talking about spatial extent being unending. The content matter, light, galaxies can be thinly spread. You can have an infinite desert and still be thirsty because the water is scarce. So to gather the threads, infinite for us means no boundary to space. Not a promise of every possibility realized, just no edge. What we can observe is limited by time and the speed of light. That's the horizon, not a physical fence. The universe can be unbounded, whether or not it's infinite in size. Flatness hints that infinite is plausible. Expansion is a change in the scale of distance, not an explosion into emptiness, not a balloon seeking a room to fill. And there is no special center of this expansion. From wherever you stand, the far landscape drifts. With those pieces in place, we can finally talk about what astronomers actually mean when they say space is expanding, and why that doesn't force galaxies to feel any wind in their hair. That's next. Space is expanding sounds like it should come with a bang, a whoosh, or at least a tug. Instead, it's more like a quiet change in the background scale, the way a map might very slowly zoom out while you keep walking. Your steps feel the same. Your shoes don't notice anything. But when you look back at the map, towns are farther apart than they were. Let's build a picture that sticks. Take a big sheet of baking dough and sprinkle it with raisins. The dough is space. The raisins are galaxies, bound to their own little communities of stars. Now put the tray in a warm oven and watch the dough rise. You'll notice two things. First, every raisin sees every other raisin moving away, on average. Second, raisins that are farther apart separate faster than nearby ones, not because those raisins are pushing harder, but because there's more dough between them to expand. That's the heart of cosmic expansion. Distances grow because the medium itself stretches. Here's what this picture doesn't say. It doesn't say a raisin can feel the dough pulling on its insides. Why? Because a raisin is held together by stickiness, its own internal binding. In space, galaxies are held together by gravity. Stars are held to galaxies, planets to stars, you to the Earth, atoms to atoms by electromagnetic forces. Those local bonds make these systems stubborn against the gentle, slow stretching of space. That's why your coffee cup doesn't get bigger with the universe, and the solar system doesn't drift apart like confetti. Expansion shows itself only over huge distances, where gravity between separate galaxy groups is too weak to win. Now, the dough is just a metaphor. Space isn't a substance in the gooey sense. You can't scoop it or weigh it in a bowl. We use the language of fabric or stretching because we need simple words for a geometric idea, the rules for measuring distance change with time. That's all. No wind, no preferred direction, no outside into which space is moving. Just a gentle, everywhere at once increase in the ruler we use to mark far-flung separations. But if it's expanding, shouldn't we be able to see things physically flying apart? We do indirectly. Distant galaxies' light arrives redder than when it was emitted, not because they're racing through space like bullets, but because the space between us and them grew while the light was en route, stretching the light's wavelength. That stretching is our quiet proof that the map has been changing scale under the beam as it traveled. Another important clarification. Expansion isn't about a single moment of fire that hurled everything outward from one spot. The Big Bang wasn't a bomb in a room. It was a hot, dense state everywhere, followed by cooling and expanding everywhere. If you were somehow there back then, you or the matter in your body was part of that state. It would have looked the same in all directions. No edge, no outside. Just a universe whose distances grow with time, revealing structure as it cools like mist, condensing into rain, then rivers, then seas. Where's the center, though? Pick any galaxy far away. Ask observers there what they see. They'll report what we do. Galaxies, on average, receding in every direction, with the farthest receding fastest. They can make the same claim we make. It looks like we're in the middle. Both statements are true, because the pattern has no unique middle. Expansion is democratic. What about the parts that don't expand? Great question. Gravity and other forces can override the overall trend when matter is dense enough and close enough together. The Milky Way and Andromeda are a good example. Despite the global expansion, the two are moving toward each other. Their mutual gravity wins locally, and in a few billion years, they'll merge. On scales of galaxy clusters, cosmic structure grows filaments, walls, and knots while the vast spaces between those structures widen. So the cosmic web tightens locally, even as the global tapestry stretches. One more gentle but important point. In the last few billion years, the pace of this expansion has been accelerating. Something in the empty parts of space acts like a uniform pressure, nudging the stretching along. We call it dark energy, not because it's spooky, but because we don't yet know its nature. We're naming an effect. For our purposes here, all you need is the picture. Over the largest distances, the zoom out is not just steady. It's picking up speed. Locally, life goes on. Globally, the map's scale bar grows a little faster with time. So when astronomers say, space is expanding, hear this. On the grandest scales, the distances between galaxies that are tightly bound are increasing with time. No explosion, no edge, no center. Just a slow, everywhere change in the measure of between. That single idea, subtle, quiet, almost boring, explains a sky full of redder light, a universe that looks similar in every direction, and the long reach of a horizon that is about time as much as about space. Now we're ready for the part that initially sounds like wordplay, but isn't. How something that's already infinite can still expand. Take an endless city laid out as a perfect grid, streets and avenues, stretching without limit in every direction. That's our stand-in for an infinite universe. No edge, no last block, just more grid. Now imagine that, very slowly, every block lengthens. The intersections stay in place relative to their neighbors. No street jumps over another, but the distance between intersections increases. Before, each block was, say, 100 meters. Later, each is 110, then 120. The city was infinite before. It's infinite after. Yet the distance between any two far intersections has grown. That's expansion without edges. A helpful way to talk about this is the zoom setting of the cosmic map. The zoom isn't your personal zoom. You don't feel it. It's a property of the map itself. When the zoom level increases, every unit of distance between far-off landmarks gets larger. The number of landmarks in an infinite grid remains infinite, but the spacing between them changes. No contradiction. Infinity doesn't care that you change the size of a unit ruler. It remains unending while distances stretch. That feels like cheating, you might think. You're saying everything gets farther, but nothing moves? Right, because we're separating motion through space from change of space. In ordinary life, things move through space cars drive, planes fly. In cosmic expansion, faraway galaxies can drift with their local neighborhoods while the space between neighborhoods grows. Locally, motion might be small or even toward each other. Globally, the separation increases because the background scale is changing. Then what is the universe expanding into? This is another place our instincts, trained by rooms and balloons, push us toward a picture with an outside. But that outside isn't required. When cartographers draw Earth's surface on a flat map, they don't need to shove the map into a bigger room. It's a change in relationships on the surface. Likewise here, expansion is about the geometry relating points within the universe, not about the universe moving into a larger container. If there is an outside, it's not part of the model we need to describe the observations. For completeness, there's also the balloon analogy. Draw dots on a balloon and inflate it. The dots move apart. None is the center, and the surface has no edge on the surface. That's good for visualizing no center, and everywhere moves apart. The catch is, the balloon has a literal outside. Our universe needn't, so use the balloon only for the relationships on it, not for the idea of an external room. But infinite's still expanding. Doesn't that mean it gets more infinite? This is where language creaks. There isn't a more to infinite area or volume in the everyday sense. Infinite just means without bound. You can double the spacing in our endless grid, and it's still endless. You can triple it, still endless. The total remains unbounded even as local distances grow. Think of counting numbers. There are infinitely many. If you remove every other number, there are still infinitely many left. Counterintuitive? A little, but it's how infinity behaves. It's insensitive to scaling and trimming that would dramatically change a finite set. A practical angle tends to tame the weirdness. When astronomers measure far galaxies' light, they're not testing philosophical infinity. They're checking how the spacing has changed over time. That change shows up as a simple pattern. The farther away a galaxy is, the more its light is stretched. That's it. The infinite versus finite debate lives beyond our horizon, and we can tuck it away without losing sleep. What matters for the paradox is that, 1, there's no edge required for expansion, and 2, an unbounded even infinite space can have its internal distances increase everywhere at once. 2 more misconceptions worth sweeping up. Expansion means everything must get stretched, not locally. The bonds holding atoms, planets, and galaxies win handily over the slow, gentle stretching of the cosmic background. Expansion is a background trend, not a force prying apart your kitchen table. There must be a center where the bang happened. The early hot state was everywhere. Expansion preserves that symmetry. Every large enough region looks statistically similar, and every place can claim the same view on average. So no privileged launch point. If your mind still wants a picture, return to the endless city. Night falls. Street lights appear, galaxies lighting the grid. You stand at one intersection and watch the distant lights drift farther apart. Very slowly. Here, you're not walking. The intersections around you aren't walking. But your mental map, the one that tells you how many blocks lie between far landmarks, keeps updating with larger numbers. The city never had an edge. It never needed a center. And still, the distances grow. That's all we need for the infinite yet expanding part. The next natural worry is personal. If space is stretching, why doesn't it tear us apart? Why doesn't it at least loosen the screws of the solar system? Let's answer that calmly. If the universe is slowly turning up the distance dial, why aren't we, our homes, our planet, even our galaxy, coming unglued? Short answer. Because local glue beats global drift. The glue here is gravity on big scales and electromagnetic forces on small scales. The drift is the gentle change in the background scale that only shows its face across truly cosmic gulfs. Think of a city again. The region-wide zoning board changes the rule that future blocks must be longer. Meanwhile, your neighborhood association, call it gravity, has you and your nearest streets bound with contracts, fences, and shared utilities. That local web keeps your cul-de-sac intact even as the blueprint for distant development stretches. You won't wake up to find your driveway farther from your front door because the city widened some arterial roads 10 miles away. Start small and climb. Atoms, electromagnetism binds, electrons to nuclei with a grip that makes the cosmic stretch laughably weak by comparison. Your atoms don't scale up with the universe. You, mountains, planets, same story. The forces holding matter together, plus gravity binding you to Earth, overwhelm the background trend by astronomical margins. Solar system. The sun's gravity holds planets in orbits like stones in a sling. The cosmic scale change is so feeble across these distances that it's utterly swamped. Planetary paths don't spiral outward because space is making more space. They follow the local rules set by the sun's grip. The Milky Way. Our galaxy is a deep lake in the cosmic landscape. Stars swirl within its gravity well. Expansion is a ripple that can't climb out of that well to yank stars apart. Where does expansion finally show? Between galaxy groups and clusters on scales, where gravity is weak and distances are measured in hundreds of millions of light years. There, the background drift wins. The cosmic web looks like this. Dense knots, clusters, connected by filaments, superclusters, with enormous voids between them. Within the knots and along the thicker filaments, gravity keeps building structure. Across the voids, distances quietly grow. A twist entered the story a few billion years ago. The expansion is accelerating. The shorthand for the nudge, causing that is dark energy, a uniform. Something woven into empty space that acts like pressure, pushing the scale to grow faster. Does that change the local picture? Not really. It's still incredibly gentle compared with the bonds inside galaxies or solar systems. What it does change is the long-term map. On very large scales, more and more distant galaxies slide beyond our ability to ever see them. Not because they hit a wall, but because the space between us stretches faster than their light can close the gap. Here are two comforting facts to pocket. The Andromeda exception. Despite global expansion, the Andromeda galaxy is actually on a collision course with the Milky Way. Local gravity wins so thoroughly that we'll merge in about 4 to 5 billion years. Expansion isn't a conveyor belt dragging everything apart regardless of circumstances. It's a background trend that locals can fight and beat when they're close and massive. No cosmic tide in your living room. There's no extra expansion force tugging on bodies the way the moon raises tides. Expansion isn't a new push you could feel. It's a slow relabeling of far distances by the geometry of space itself. If nothing resists on very large scales, separations increase. Where forces tie matter together, they keep doing so. One more analogy with traffic helps. Imagine a highway whose speed limit is gradually increasing with distance from the city. Farther out, cars are, on average, moving faster apart from each other. Inside your neighborhood streets, though, the speed limit doesn't change and local traffic rules dominate. Expansion is the highway rule. Gravity and electromagnetism are the neighborhood ordinances. So no, galaxies aren't ripping, atoms aren't stretching, and coffee mugs aren't growing. Expansion is the macro behavior of empty space between huge structures. It's patient and subtle, visible not in our hands, but in the color of ancient starlight, and in the way clusters drift over eons. With the personal worries settled, we can lean into the big picture again. We've said no center and no edge. We've separated motion through from change of, and we've placed expansion where it lies between the biggest things. Next up, will put your mind right at the limit, the horizon itself. What does it mean that parts of the universe can be forever out of reach, even if the universe has no walls? And how does that tie back to the first question, the paradox that sent us on this late-night walk in the first place? Let's walk right up to the idea of a cosmic horizon and put our hands on it well, not literally, because there's nothing there to touch. Our horizon in cosmology isn't a wall in space. It's a limit in connection. It marks how far signals light, neutrinos, gravity's ripples, could have reached us since the universe began. Anything farther simply hasn't had enough time to say hello. A good way to picture it is to stand on a quiet shore and look out to sea. You see a crisp line where the ocean seems to meet the sky. You know the Earth doesn't end at that line, but your view does. The cosmic horizon is like that, but the reasons are deeper than just curvature and air. They're about time and expansion. The universe has a finite age. Light travels at a finite speed. Meanwhile, space itself has been stretching under that light like a moving sidewalk. Put those together, and you get a moving limit. How far news from the cosmos could reasonably have reached us? So there are two ideas to separate. The observable universe, everything from which light has already arrived here since the hot, early beginning. It's a time capsule, a layered onion of past scenes. The farther out you look, the further back in time you're seeing, because the light took longer to get here. A distant galaxy isn't over there right now, in your telescope. It's back then. Telescopes are time machines. The whole universe, whatever exists beyond our current view, may be a lot more of the same, may be structured differently, may be truly infinite. This isn't philosophy for its own sake. It matters because we often mix up all that exists with all we can see, and that's how paradoxes sneak in. Here's a subtlety that trips everyone, including professionals. Early on, because space expands, the distance to the place that sent us a photon can be larger now than the naive speed times time would suggest. Imagine a friend standing on an escalator, moving away from you, while tossing a ball toward you. They throw the ball. It comes, but the escalator keeps carrying them farther away the whole time. When you finally catch the ball, your friend is farther than throwing speed times seconds. In the universe, the escalator is the expansion of space, and the ball is a photon. That's why you'll hear two different sounding statements that are both true. A, we're seeing light that's been traveling for billions of years. And B, the place that emitted that light is now much farther away than that many light years. The travel time is about the journey. The present distance is about the escalator that never stopped. Another horizon flavor shows up when expansion accelerates. We'll keep coming back to this. Even if you wait forever, there can be regions that will never send you anything new, because the space between you and them grows so fast that fresh light they emit now will never close the gap. That's called an event horizon. Think of it as the boundary between things that can ever influence us again and things that have effectively slipped beyond contact. It's not a hard shell. It's a limit set by the competition between light speed and the pace of the stretch. Why do horizons matter to our big question? How can an infinite universe expand? Besides sounding cool? Because they explain how no edge and limited view happily coexist. You can have an endless plane and still be stuck with a circle of lantern light. Tonight, our lantern grows as time passes, bringing in whispers from farther fields. Yet some lanterns on distant hills are carried away faster than their glow can reach us. Both things are true at once. A few common confusions. Gently cleared. Can we travel to the horizon? Not really. The horizon isn't a place. It's a now limit. As time passes, your horizon changes even if you stand still, just because more light has time to arrive. And also because expansion shifts, which regions are drifted out of reach. You can walk to the edge of a lake, but you can't walk to the edge of a time boundary. Is the horizon the same in every direction? On average, yes. The universe looks almost the same in every direction when you smooth over local lumps. That's an observation, not a creed. The little differences we do see, tiny temperature ripples in the afterglow of the Big Bang, are the seeds that grew into galaxies and clusters. Uniformity with interesting freckles. Does the horizon mean the universe started from a point? No. The early hot state was everywhere. The horizon describes how far causal contact could have spread then, not a central launching spot. No cosmic bullseye defined. There's beauty here if you let it sink in. Our sky isn't a static dome, but a layered record nearby stars, blinking in the recent past. Galaxies showing us teenage years of the cosmos. A faint glow from when atoms first formed. Farther still the fog of the almost beginning. All of that fits inside a horizon, set by time's patience and the universe's stretch. Beyond the line, more land, no fence. Just places that haven't and maybe never will reach our shore. Hold that feeling. It will help when we tackle the next source of head scratching. People say, distant galaxies are receding faster than light. Isn't that illegal in the laws of physics sense? Let's switch on a softer lamp and sort that out. Faster than light is a phrase with alarm bells attached, so let's diffuse it carefully. Einstein's speed limit. No information or object can move through space faster than light still stands. What expansion gives us is something else. Recession speed, which isn't motion through space, but the increase of distance because space itself is changing scale. Those sound similar, but they're not the same ticket. Use a moving walkway again. Two friends stand on different sections of a very long conveyor that's speeding up with distance. Neither friend runs. Neither breaks any local speed rule. But the gap between them can grow faster than either could sprint, because the walkway under them is doing most of the work. That gap growth is a recession speed. It's not anyone outrunning light locally. It's the geometry underneath stretching. Back to the universe. Over truly vast separations, the stretching can make the distance between unbound galaxies grow faster than light. No law is broken. No spaceship is leaving its local patch faster than a photon. The rule nothing outruns light is about local motion. Expansion is about global geometry. Okay, but can light from those super-fast receding galaxies ever reach us? Subtle answer. Sometimes yes, sometimes no, depending on when the light was emitted and how the expansion sped up or slowed down during its journey. Picture tossing a ball slightly uphill while the hill is very slowly rising. If you throw it early enough and hard enough, light released when the expansion was slower, it can still reach you even if later the hill rises faster. Acceleration kicks in. Light that starts too late might never arrive. That divide is what we call the event horizon. It separates, can ever see new signals, from forever out of causal reach. This is where those pretty red shifts in galaxy spectra do double duty. They're not just speedometers. They're also mileposts on a changing road. The more the light is stretched, the more total stretching history it experienced on the way here. That ties directly to how the gap between us and the source was evolving while the photon crossed it. It's like reading tree rings, but with wavelengths. Does any of this affect me, personally? Not in your bones. Local life is governed by local physics. Gravity holding your feet to the ground. Electromagnetism holding your atoms together. The sun's gravity holding planets. Expansion's ability to produce faster-than-light separations is an ultra-long distance feature. It needs deep space and lots of time to show its colors. There's one more mental itch to soothe. If far galaxies recede faster than light, how did we ever see the cosmic afterglow, the very early light from when the universe became transparent? Shouldn't that be impossible? Here's the trick. That ancient light set out when everything was much closer, and expansion was not yet accelerating. The light had a head start. It's been traveling ever since, through an arena that changed under it. Along the way, expansion stretched it into microwave wavelengths That's the microwave background part, and thinned its energy. The fact that we see it now is a testament to timing, not a violation of any limit. A practical summary to pocket. Local rule stands. Nothing moves through space faster than light. Your rocket, your signal, your neutrino still kept. Global effect differs. The distance between unbound regions can grow faster than light because the ruler itself is changing. That's recession, not racing. Horizons sort the mail. Some regions can no longer send us fresh news, not because of a wall, but because the gap grows too quickly for new light to bridge. Old news that left earlier can still arrive. Let's pause for perspective. People sometimes feel small or stranded when they hear about horizons and unreachable realms. Flip it around. We live in a universe that allowed anything to talk to anything at all across unimaginable distances. For billions of years, light has carried stories from the deep past to our little rock. We've built tools that catch those whispers. Even the parts we'll never contact again contributed their early chapters to the messages we see now. We're not cut off. We're included. With that calm in place, we can ask a natural follow-up. How did the universe get so smooth and coordinated at large scales that these explanations even make sense? Why does the sky look nearly the same temperature in opposite directions if those regions couldn't talk to each other early on? There's a proposed prequel to the hot early universe that answers that, and it has a friendly name: inflation. Let's open that door carefully and keep it human-sized. Imagine you walk into a bakery at dawn. Every loaf on the rack front, back, left, right looks nearly the same. Same crust, same rise, tiny differences that will matter later, but overall a uniform bake. You might ask, how did the baker get them so consistent? Now swap bread for the cosmos. When we look at the sky's ancient afterglow, the cosmic microwave background, we find it astonishingly uniform in temperature across huge swaths of sky, with only tiny ripples. That uniformity demands an explanation. How did parts of the early universe, now far apart, end up so well coordinated? The leading idea is called inflation. It proposes that before the hot, dense phase we call the Big Bang's aftermath, the universe underwent a brief, wild period during which space expanded enormously and very rapidly, far faster than today's gentle stretching. Not because something exploded, but because the energy of empty space drove a runaway growth spurt. Then that special energy relaxed, dumping its contents into the hot soup that later cooled into atoms, stars, and galaxies. Think of inflation as the preheating cycle. It set the conditions so that the bake would be even when the real cooking began. Two big wins come out of this story. Smoothing. Before inflation, a small, causally connected patch could settle into a nearly uniform state-like batter mixed to an even consistency. Then inflation ballooned that tiny patch to a size vastly larger than our observable universe. Result: our sky looks the same in every direction because it came from one well-mixed region stretched beyond our horizon. The tiny remaining lumps, the little temperature ripples we measure, are exactly what you get from small fluctuations blown up to cosmic scale. Seeds for structure. Inflation doesn't erase all differences. Quantum jitters microscopic, random wiggles get magnified into slight overdensities and underdensities in the early universe. After inflation ends and the universe returns to calmer expansion, gravity slowly amplifies those overdensities. Over billions of years, they grow into the cosmic web, galaxies, clusters, filaments. The freckles in the sky's baby picture become the skeleton of everything we see. We don't need the machinery under inflation's hood tonight. It's still an active research area with multiple candidate engines. What matters for our walk is what inflation buys us. A reason the cosmos is so uniform on the largest scales, and a mechanism for why it's not perfectly uniform, giving structure a place to start. It also helps explain why space looks so flat overall, why triangles drawn on the largest canvases appear to have the familiar 180 degrees, because inflation would have stretched any initial curvature toward flatness. The way zooming into a huge sphere makes your local patch look like a plane. Does inflation change our answers about infinity and expansion? It doesn't have to. Inflation is about a very early spurt that made our observable patch vast and smooth. Whether space is truly infinite or just very, very large remains an observational question. Inflation can be compatible with either. The infinite yet expanding logic still holds. The scale can increase everywhere, with or without edges, and your horizons still reflect time and stretch. A couple of friendly cautions. Inflation isn't a license for anything goes. It's not a multiverse vending machine in this conversation. Some versions of inflation allow for ideas like multiple regions with different properties, but those are speculative branches. We don't need to climb for tonight's goal. The simple version, a brief, rapid expansion smooth and seeded our patch, already illuminates a lot. Evidence matters. Inflation is attractive because it neatly accounts for patterns we measure in the cosmic, microwave background and the distribution of galaxies. But cosmologists keep testing it, sharpening models against data. That's the ongoing dance. Idea meets observation. Here's a softer way to hold it all. The universe had a quiet plan for consistency. Not a conscious plan, but a physical process that made distant parts share the same starting notes before they drifted apart. Later, the orchestra spread across the stage, yet the instruments kept the tune. Inflation is our name for the rehearsal that made that possible. If inflation made space so nearly flat and so uniform, we can finally ask the shape question you've probably been saving. What is the shape of the universe? Is it curved like a sphere, saddle-shaped? Or truly flat and endless, like our endless city grid? And curveball, could it be finite yet edgeless, like a video game world that wraps around? Let's talk shapes without turning math class back on. When we say shape of the universe, we're not picturing a bubble floating in a bigger room. We're asking a quieter question. If you drew huge triangles by connecting distant galaxies with imaginary straight lines, would the angles add up to 180 degrees, flat, more than 180, positively curved, sphere-like, or less, negatively curved, saddle-like? That's a way to test the geometry of space itself. Observations, especially of the cosmic microwave background, suggest that on the largest scales we can see, space is very close to flat. Triangles add up right. Parallel lines behave the way your schoolbook promised. That's compatible with an infinite universe, like an endless plane. And this is where it gets fun. Flatness alone doesn't force infinity. You can have a flat space that is finite by giving it a topology that wraps around, like a classic video game map, where leaving the right edge brings you in from the left. Mathematically, that's like a torus, a donut shape, but flattened. The geometry is flat locally. The connections make it finite and edgeless globally. Think of an ant walking on such a wraparound floor. The ant never finds an edge. It just loops without realizing it, because its world is stitched in a clever way. If our universe were like that, you could, in principle, look far enough in just the right direction and see a faint, ghostly version of our own galaxy from the other side light that took the long way round. People have looked for those repeating patterns in the sky's afterglow. So far, no convincing repeats. That nudges us toward the simpler conclusion. Either space is truly infinite, or it's so large that any wraparound is far beyond what we can probe. If we set the wraparound aside for the moment, the three broad options are: flat, zero curvature, like an endless grid. No edges required, distances measured the way you expect. Expansion changes spacings, not shape. Positively curved, like a sphere's surface. Finite, but unbounded. Walk straight long enough, and you'd return to your start. Expansion would be like the sphere's radius growing with time. Negatively curved, saddle-like. Infinite and open, with geometry that diverges. Triangles have less than 180 degrees. The balloon analogy we used earlier sneaks back here. Its surface is positively curved and finite, yet edgeless on the surface. Inflate, and that surface expands. Again, ignore the balloons outside. Focus on the rule, no edge from the inside. Our universe doesn't have to be spherical, but you can borrow the finite, but without a border idea from it. Why does shape matter for our paradox? Because infinite yet expanding has to be true for any of these. Even if the universe were finite and unbounded, you could still have expansion. The radius or the wraparound scale can grow, increasing distances everywhere, without any need for an edge. If the universe is infinite and flat, scaling up the grid leaves it infinite while growing separations. If it's negatively curved and infinite, same story. Expansion is about the scale, not the extent label. Now, how do we actually check shape without drawing galaxy triangles big enough to make a geometry teacher cry? One clever way is to use the cosmic microwave background as a standard scribble. There's a characteristic size imprinted in those baby sky ripples, the scale of sound waves frozen into the early plasma. We measure how big that feature appears on the sky. If space is flat, it subtends a certain angle. If space is positively curved, it looks bigger, like lines on a globe appearing broader to you. If negatively curved, it looks smaller. The measurements line up with flat, within small margins. Even so, don't let flat trick you into thinking boring. Flat space can host all the drama. Galaxies merging, clusters dancing, voids yawning. And flat space can be both infinite or cleverly finite, depending on topology. What flat does do for our question is simplify it. In a flat, expanding universe, distances grow everywhere. No edges, no center, no contradiction with infinity. Clean. One last toy model. Take a classic tiled floor pattern that goes on forever in imagination. That's flat, infinite, no edge. Now install an architect's spell so that every so often, every tile expands slightly. The pattern stays a pattern. The floor stays edgeless. The spacing grows. No weirdness needed, just a changing scale. We've collected quite a few pieces now. Horizons, recession versus racing, an early smoothing, inflation, that explains the evenness, and a mostly flat stage where the whole story plays out. The natural next move is to pull these threads together and return to the original knot. We asked, how can the universe expand if it's already infinite? Let's answer that crisply, in plain language, and tuck in a few "so what?" reflections that make the question feel human again. Time to tie the bow without fancy knots. Here's the straight answer you can carry around. Infinite in our context means no edge. It says nothing mystical about more than everything. It just means you can keep going and never hit a border. Expansion isn't things exploding into emptiness. It's the scale of space changing so that far apart landmarks drift farther apart everywhere at once. Like a map slowly zooming out while the towns on it keep their relative layout. Those two ideas don't clash. An edgeless map can still change its zoom. An endless city grid can still lengthen its blocks. Infinity doesn't forbid the ruler from changing. That's it. The paradox dissolves when we stop treating expansion like a blast from somewhere into somewhere and treat it as a quiet rescaling of between. No center required, no outside needed, just geometry evolving. If you want a sentence to share with a friend tomorrow, try this. The universe can be infinite in extent and still expand, because expansion is not about reaching an edge. It's about every far distance growing, like dots on stretchy fabric. If your friend says, "but faster than light," you add, "that's recession speed from stretching, not racing through space." Locally, nothing outruns light. If they ask about a center, you say, "Everywhere looks like the center, because the pattern is the same in all directions on large scales." If they worry about atoms stretching, you finish. Local glue beats global drift atoms, planets, and galaxies are bound. So what? Why does any of this matter after the yawn? Because it reframes your place in a way that's both humbling and strangely comforting. You're not sitting at the rim of an explosion. You're sitting inside a process that is patient and everywhere, one that carried whispers from the young universe across billions of years straight into your night. The faint microwave glow filling space is the oldest light you'll ever see. It got here not by breaking rules, but by leaving early and traveling while the stage beneath it changed. A galaxy's red light isn't sad. It's a receipt proof that the scale has been changing the whole time. It also answers a classic head-scratcher you might have heard. If the universe is infinite with infinite stars, why is the night sky dark? One big reason is that the universe has a finite age, and it's expanding, which stretches and thins distant starlight. Not every line of sight is filled with blazing suns whose light had time to arrive unchanged. The darkness isn't a bug. It's a clue. And then there's the horizon. Not a fence, just a limit of contact. It explains why the universe can be bigger than we can see without needing an edge to hide behind. The horizon grows as time passes, letting us read deeper chapters. At the same time, the acceleration of expansion gently closes the book on some faraway future chapters. We'll never receive new light from certain regions again. That's not a tragedy. It's a rhythm. We were always going to live inside a finite window of influence. And within that window, the universe gave us enough to wonder at for 1,000 lifetimes. Here's a final image to keep. Picture an endless field of lanterns at dusk. You hold one lantern. So does every distant traveler. As the evening deepens, the air between lanterns seems to stretch. Far lights drift farther. No one is running. No one's wick burns faster than the rules allow. Yet the pattern changes. Some lights will always be too far for their fresh glow to reach you. Others were close enough, early enough, to send their rays that you see now as a faint wash on the horizon. The field has no fence. The drift has no center. You are not outside of it, you are part of it. So when the big question returns, how can the universe expand if it's already infinite? You won't need to wrestle. You'll just shrug gently and say, because infinity is about edges, and expansion is about scale. One can be endless while the other changes. Then you can let the thought do what this series is for. Slow your breathing, widen your sense of time, make room for sleep. If you're still awake, don't worry. We're not done exploring. Ahead we'll meet the universe's baby picture more closely, peek at how galaxies learn to gather, and ask how the far future plays out under that steady, accelerating stretch. But for now, you've untied the hardest knot in this whole topic. That's enough for one night. If you could take a baby photo of the universe, you'd frame it in microwaves and hang it on every wall of the sky. Astronomers actually did, and it's called the cosmic microwave background, the CMB for short. It isn't a single dot or a streak. It's a faint, even glow that arrives from every direction, all the time, like the softest static you can imagine. And hidden in that glow are tiny speckles temperature bumps only a few parts in 100,000 that turned out to be the universe's first fingerprints. Roll the clock back to when the cosmos was just a few 100,000 years old. Not stars, not galaxies, just a hot, bright fog made of light and charged particles. In that fog, light couldn't travel freely. It was constantly scattered, like car headlights in thick mist. Then the universe cooled just enough for electrons to settle into atoms. The fog cleared. Suddenly, light could go. The very first photons to slip free have been traveling ever since, stretched by expansion from brilliant early light into today's microwaves. That's the CMB, a snapshot of the moment the cosmos became transparent. What's remarkable isn't only that we can see it, but what it says. First, it tells us the big picture was astonishingly uniform. Opposite sides of the sky regions that are now so far apart, they could never trade a text, have almost exactly the same temperature in that afterglow. That smoothness is one of the clues that led us to the idea of early inflation, a brief era when a small, well-mixed patch was blown up to cosmic scale. Second, those tiny ripples in the CMB aren't noise. They're the seeds. Slightly denser spots and slightly thinner spots. Gravity favors the dense ones, slowly pulling more matter in. Over billions of years, ripple becomes thread. Thread becomes web. Galaxies, clusters, and great empty voids between them. When you look at the modeled CMB map, you're looking at the universe's blueprint, minimalist, but predictive. People often ask, if that afterglow is everywhere, where do you point a telescope? Answer, anywhere. The CMB is all over the sky. We built instruments to subtract local clutter, the Milky Way's glow, nearby dust, and what remains is the background itself, almost perfectly even with those exquisite speckles. Different missions have sharpened the picture over the years, each one confirming the main story and adding detail. How big the ripples are, how they line up, how flat the stage appears to be. Another common question, why microwaves? Because expansion has been stretching those photons for more than 13 billion years. Think of a cello string lowered until it purrs almost below hearing. Same note, different register. The universe didn't change the message, just the pitch. There's a poetic limit here, too. The CMB isn't the beginning. It's the earliest light we can see. Before that, the universe was opaque. You can think of the CMB as the inner surface of our visible sphere, the last scattering of that ancient fog. Beyond it in time, more story, but not in light. We study those earlier chapters indirectly, through patterns left behind, like footprints in cooling lava. The CMB also turned out to be a measuring stick. Those speckles aren't random sizes. Their typical scale set by sound waves sloshing in the early plasma gives us a known yard. Measure how large that yard appears on the sky, and you've learned about the shape and expansion of space itself. That's one reason we're confident the universe is nearly flat on big scales. The yard looks just the right size. Here's the human part. There is something deeply calming about knowing the night isn't dark because nothing is there. It's dark because ancient light has been softened and spread thin, while the oldest light of all is still quietly arriving from everywhere at once, telling us that the whole sky shares the same origin story. You, lying there with your eyes closed, are bathed in a glow that began its trip long before any star we can see was born. The universe has kept the receipt, and it's readable. So the baby picture is not a monument. It's a map. Next, we'll trace how those tiny ripples grew into the cosmic web, how empty space learned to have structure, and how gravity and cooling gas teamed up to light the first stars. Start with that almost smooth sky. Take a ripple that's a hair denser than average. Gravity gives it a tiny advantage. More matter rains in, the ripple grows, not fast cosmic patience fast. Meanwhile, the thinnest regions fall further behind, becoming the voids between future structures. Over time, the universe organizes into a web, filaments, knots, and vast empty reaches. If we could turn our Milky Way transparent, we'd see this scaffolding stretching out in every direction, a 3D lacework of galaxies beating the threads. Several ingredients make this happen. Gravity is the lead. It doesn't care what the matter is made of. It pulls on mass and energy alike. Once a region gains a slight edge, gravity amplifies it. The more matter gathers, the deeper the well it digs, and the more it invites in. Radiation pushes back at first. Early on, the universe is hot and light is energetic. That pressure resists collapse. But expansion cools everything, and eventually radiation's push fades compared to gravity's pull. Gas cooling is the quiet hero. Even if gravity gathers gas into a cloud, that gas needs to shed heat to tighten further. When it can radiate energy away via atomic processes, it contracts, densifies, and crosses thresholds where stars can ignite. No cooling, no stars. No stars, no heavy elements. No heavy elements, no planets or people. The first stars were likely massive and brief, flooding space with new light and new elements, seeding the next generations. The web doesn't grow evenly. Some regions become cluster city centers of the cosmos, where hundreds or thousands of galaxies mingle in deep gravitational wells. Between clusters, filaments the highways carry matter along. In between, voids the countryside are surprisingly empty. Not absolute nothing, but close enough to let you appreciate contrast at a universal scale. As galaxies settle within this web, they don't stay pristine. They merge. Big ones grow by swallowing small ones. Collisions are common, but because galaxies are mostly space, stars rarely hit stars. The drama happens in the gas-shocked, compressed, stirred into fresh starbursts, and in the invisible halos we'll meet next. Supermassive black holes at galactic centers feast on inflowing material, and sometimes blow out jets that can regulate a galaxy's growth, like thermostats with very dramatic plumbing. There's a beautiful echo from the CMB here. The same sound waves that left a preferred ripple scale in the baby sky also left a subtle ripple in galaxy clustering, a faint preference for galaxies to be separated by a certain large distance. It's called a standard ruler, and it lets us read the universe's expansion history later on, the way a geologist reads strata in a cliff. It's helpful to let go of the idea that structure formed on top of an expanding universe, as if those were separate stages. Expansion and growth ran together, always competing. On small scales where gravity and internal binding are strong, structure wins and decouples from the drift. On large scales where gravity's net pull is weak, expansion dominates, quietly widening the spaces between superclusters. The timing is generous. Stars and galaxies didn't appear overnight. The first stars likely flickered to life a few 100 million years in. Galaxies assembled over the next billions. Our sun arrived late to the party, forming when the universe was already more than 2/3 its current age. That lateness is a feature, not a bug. It meant previous generations had time to cook heavier elements and scatter them, so our solar system could have rocky worlds and chemistry, interesting enough to wonder about all this. If you squint at the big picture, the story is pleasantly simple. Tiny differences grew into large patterns. Gravity pulled, gas cooled, stars lit, galaxies merged, black holes sculpted, and the web we now map took shape. The details are rich, and ongoing astronomers are still learning how feedback from stars and black holes shapes galaxies, how gas flows along filaments, how star formation waxes and wanes. But the broad arc is as steady as a heartbeat. Now, something crucial has been guiding this whole process from the shadows, providing most of the gravity, setting the scaffolding, but refusing to shine. You've heard its nickname. It's time we give dark matter its quiet due, and along the way explain why coffee mugs, planets, and galaxies don't get tugged apart by cosmic stretch. Dark matter sounds like a mood, but it's really an admission. Most of the matter that tugs on galaxies doesn't glow, reflect, or absorb light in any way we can see. We infer it from its gravity. Spiral galaxies spin so fast that if you only count the visible stars and gas, their outer parts should fly apart. They don't. Something unseen supplies extra pull. Clusters of galaxies bend background light, the universe's version of a magnifying glass more strongly than visible matter alone would allow. Added up, and roughly 5 times more matter is dark than familiar. What is it? We don't know yet. It seems not to be ordinary stuff hiding in the dark. No swarm of cold planets or burnt-out stars can make the numbers work. The simplest idea is that it's made of new, slow-moving particles that barely interact except through gravity. Whatever it is, dark matter doesn't clump into disks like gas does, because it can't shed heat by radiating. Instead, it forms large, Puffy halos and visible cocoons within, which galaxies like ours assemble. This invisible scaffolding changes the whole growth story. Those tiny density ripples in the early universe included dark matter as well as ordinary matter. Because dark matter started collapsing first unbothered by radiation pressure and not needing to cool veil light, it built the backbone of the cosmic web. Ordinary gas then fell into that skeleton, cooled, and lit up as stars. Without dark matter's early lead, structure would have been slower and slighter. With it, the web is bold. And here's the promised explanation for why local things don't expand with the universe. Cosmic stretch is very real on huge scales, but binding forces dominate small ones. The Milky Way and its dark halo are gravitationally glued together. A solar system is glued more tightly still by the sun's gravity. Your body and your mug are held together by electromagnetic forces at the atomic level, far stronger than the feeble, cumulative effect of expansion across a few centimeters. Once a system becomes bound, it's like a team of hikers roped together. The mountain may be moving under everyone slowly, but the rope keeps the group at fixed separations. A felt sense might help. Imagine a rubber sheet slowly stretching in all directions. Coins sit on the sheet. If they're just resting loosely, they drift apart as the sheet expands. But if you wrap elastic bands tightly around a handful of coins, that bundle resists the stretch. The bands absorb the pull and keep the coins together. Gravity and electromagnetic bonds are our elastic bands. The sheet can keep stretching. The bundles stay bundles. This is why it's perfectly consistent to say the average distance between far-flung galaxies increases, while also saying galaxies, stars, and atoms don't swell. Expansion is not a wind pushing on things. It's a change in the background scale that only shows up where no stronger glue is at work. Dark matter adds one more calming note. It doesn't seem to care about the expansion directly. It rides along. Its halos form, merge, and settle under gravity's rules. Within those halos, galaxies can lead busy lives largely insulated from the grand stretch beyond their edges. We live inside such a halo, inside such insulation. The cosmic web shifts slowly on human timescales. Your dinner plate does not. There's a second shadow player, though, and it does not behave like matter at all. If dark matter builds and binds, this other ingredient accelerates the stretch of space itself, like a hand turning the dial on our moving walkway. That hand goes by the placeholder name dark energy. We don't know what it is in a deep sense, but we know how it acts. Let's meet it with the same calm we brought to dark matter. The discovery landed like a soft thunderclap. Distant stellar explosions reliable. Standard candles looked fainter than expected, as if the universe had expanded more during their light's journey than our best simple models predicted. The natural read was surprising but clear. The expansion of the universe isn't just continuing, it's speeding up. Something in the cosmic mix is acting like an anti-gravity on large scales, pushing space to stretch faster over time. We call that something dark energy. The name is honest about our ignorance. It's not a special kind of fuel we can siphon. It's a behavior. On average, empty space carries an effect that causes expansion to accelerate. The simplest version is that empty space itself has a tiny, uniform energy often called the cosmological constant that doesn't dilute as the universe expands. Matter gets thinner. Radiation thins and loses energy to stretching. But this background term stays put. So long after matter has spread out, the constant wins, turning a gentle widening into a steady acceleration. That's the headline. The consequences ripple through our earlier ideas. Event horizons become real players. In a universe with accelerating expansion, there are regions that no new light can ever cross to reach us, no matter how long you wait. Not because we're moving away too fast, in some rocket sense, but because the space in between grows too quickly for new signals to gain ground. That's the horizon we spoke about, now with teeth. Large-scale structures stop growing, Gravity keeps working where it's strong inside galaxies and clusters. But between the biggest clumps, acceleration stretches space faster, and gravity can pull fresh matter across. The cosmic web's skeleton freezes at the largest scales. Collapsed structures keep evolving internally. The map's broad strokes stay put. The night slowly empties. Over very long times, more distant galaxies slip beyond our event horizon. Their new light won't ever get here. The ones we still see grow redder and fainter as expansion keeps stretching their photons. Locally, life goes on. Globally, the sky simplifies. If dark energy is the cosmological constant, its effect is featureless and smooth. It doesn't clump. That's why you don't feel it in your house or your galaxy. Gravity's local glue overwhelms any such whisper. Dark energy is a background trend, not a local gust. Could it be something more exotic, like a new field that changes slowly over time? Possibly. People have built models where dark energy evolves, weakens, or strengthens. For our purpose tonight, we only need the current, measured behavior. Right now, the expansion is accelerating and has been for billions of years. Whether that continues forever is an open question one will keep in mind when we talk about the far future. You'll often hear the cosmic energy budget summarized like this. A small slice, only a few percent, is the stuff we know and love. Atoms, stars, gas, dust, you. A much bigger slice is dark matter, the invisible scaffolding adding up to roughly 5 times the ordinary matter. And the dominant slice is dark energy, something like 2/3 of the total, steering the long-term expansion. Don't get hung up on the exact numbers tonight. The spirit is that the familiar is not the majority, and yet the familiar is where all the interesting local chemistry and meaning happen. There's humility in keeping dark energy as a label rather than a story we've already solved. It reminds us that cosmology isn't mythology. It's a work in progress. We read the sky. We infer the trend. We test it with different yardsticks. Supernova, the pattern in galaxy clustering, the CMB's subtle signatures. Each test, so far, points the same way. Acceleration. If you want a single sentence to hold, dark energy makes the map keep zooming faster. Not everywhere noticeable, not to your coffee cup, but to the spaces between the grandest landmarks. It sets the stage for a quieter, lonelier future if it keeps behaving as it does. Which brings us gently to that future. What happens to an expanding, possibly infinite universe under steady acceleration? Do things end with a bang, a crunch, a tear, or simply a long exhale? Let's dim the lights a little more and walk forward in time. Short version. If dark energy stays constant, the universe doesn't end with drama. It thins out. Star formation dwindles. Distant galaxies fade beyond contact. Locally, bound islands galaxies and the small families they form keep their internal lives for a very long time. It's sometimes called the Big Freeze, but that makes it sound instant. It's anything but. Think more like an eternally late autumn. Quiet, prolonged, and spread over timescales our language barely covers. Here's the longer, kinder walk. In the next tens of billions of years, galaxies in our local group, the Milky Way and Andromeda foremost, will likely merge, forming a single, larger home island. Star formation continues for a while as gas clouds collide and compress, but the overall fuel supply wanes. Stars are efficient, but not perfect. Each generation locks some mass away in long-lived, faint stars and stellar remnants. The gas reservoir shrinks. New stars become rarer. Meanwhile, expansion keeps doing its distant work. More and more galaxies pass beyond our event horizon. We still see their old light, the light that started toward us long ago, but no new signals from them will ever arrive. The observable universe becomes a collection of closer and closer neighbors, with the far tapestry redshifting into darkness. If you were an astronomer born deep in that future, your sky would be misleadingly simple. The clues we use today to infer the Big Bang CMB, galaxy recession, would be vanishingly hard to detect. Cosmology would look like local weather. On even longer timescales, star formation peters out. The bright, short-lived stars die first. The red dwarfs stingy, long-burning carry the flame for trillions of years. Planetary systems evolve, drift, sometimes destabilize. Black holes slowly feast on what falls within reach, then spend eons evaporating by our faint quantum glow. If certain particle decays happen, even matter itself might have an expiration date. If not, protons could endure essentially forever. In either case, the trend is the same. Entropy rises, usable energy spreads thin, gradients flatten. Not an apocalypse, a settling. It sounds bleak until you remember two things. First, these arcs are astronomically long. The universe is patient beyond any sorrow we can meaningfully attach to it. Second, none of this steals a single sunrise from us. The fate of far future light says nothing about the value of the light you have now. Could the story be different? Possibly. If dark energy changed character waned, switched off, or reversed long-term futures would change with it. Slow down the acceleration and distant structures could drift back into causal reach over inconceivable spans. Reverse it strongly enough, and the universe could eventually recollapse. Spin the dial too aggressively the other way, and you get a hypothetical big rip, where even bound structures get torn as the scale factor accelerates wildly. Current evidence favors the calm middle, a steady, constant push, no rips, no crunch. And there's a quieter twist. Even in a future where the sky empties, local meaning doesn't have to. Civilizations, if they rise and persist, live on bound islands where gravity keeps the neighborhood together. Chemistry still works. Stars still shine for a very long time. Energy can be harvested, stored, shared. Stories can be told. The universe isn't obligated to keep us entertained with distant fireworks. It already gave us a first act packed with clues and the tools to read them. If you want one more grounding image, imagine standing on a shoreline at dusk with friends. Far boats' lanterns wink and drift, some fading below the horizon. Your own circle of light stays warm. The ocean didn't end where the lanterns disappeared. Your connection did. That's the accelerating universe, not an ending, but a slow narrowing of conversation across impossible distances. We began with a puzzle. How can an infinite universe expand? And followed its threads into horizons, baby pictures, hidden scaffolding, and the soft hand that nudges the map to zoom faster. You've seen how the paradox dissolves, how local life wins against global drift, and how the long future, while quiet, is generous with time. If your eyes are heavy now, let them close. The lanterns you can still see are more than enough. And if you're still awake, we can keep walking. There are everyday questions this cosmic picture answers. Why the night is dark. Why the sky's afterglow is so uniform. Why galaxies come in families. And how all of it loops back to your ordinary day in small, surprising ways. Why is the night sky dark if there are so many stars? That old chestnut even has a name, Olber's paradox, and it's sneakily deep. If space were eternal, static, and filled uniformly with stars, every line of sight would end on a star surface. The sky would blaze like the face of the sun. But you've looked up. It doesn't. It is mostly deep, gentle black, punched with points of light. The resolution of the paradox turns out to carry the fingerprints of everything we've discussed. First, the universe has a finite, luminous past. Stars haven't been shining forever. There was a time long ago when there were no stars, just hot plasma, then cooling gas. Light takes time to travel, so some directions simply don't have time to send you starlight yet. Darkness isn't the absence of things. It's a time delay map. Second, space is expanding. Light that set off toward us billions of years ago has had its waves stretched along the way. Blue becomes red. Red slides into infrared. Infrared can slip further into microwaves. Some starlight has been shifted out of the narrow slice of colors our eyes can see. That stretch doesn't erase the light. It softens it, spreads its energy thin, tucks it under the threshold of human vision. Third, stars aren't spread perfectly uniform and eternal anyway. They live in galaxies, and galaxies live in a web punctuated by wide voids. Stars are born, shine, and die. They don't tile the sky like bricks. Even if the cosmos were infinite in size, the combination of finite star ages and expansion prevents the sky from saturating with sun brightness. Dust doesn't solve the paradox. Dust heats up and re-radiates. If dust alone blocked starlight, the sky would glow in infrared like a warm blanket. We do see infrared glow, but not enough to make midnight noon. The real culprits are those first two, time and stretch. There's a lovely bonus twist. The night isn't truly black. It has a floor, a universal afterglow, the cosmic microwave background. That baby picture light is the smoothest wallpaper in existence, and it arrives from every direction. Your eyes can't detect microwaves, but your radio can. In a very literal sense, every night is bright, just at a pitch your biology doesn't play. You can test pieces of this paradox yourself with small, everyday analogies. Stand in a dense forest and look outward. If trees extended forever with constant density, your view would be all bark. In real forests, the trees start somewhere, stop somewhere, and thin out. Gaps remain. The sky sneaks through. Or think of a city at night, seen from an airplane. Lights seem everywhere, but distance dims them, air scatters them, and beyond a certain radius, the grid drops away. Darkness is information about limits. When people first hear the expansion explanation, they sometimes ask, so if the stretch keeps dimming things, won't everything just vanish? On our local island, no. Your neighborhood star is bound to you by gravity. Your lamp is bound to you by electromagnetism. Expansion is not a wind that blows out candles. It's a slow increase in the metric, the ruler we use for distant distances, that only shows itself across enormous reaches where no stronger glue is at work. The night sky is dark, not because your backyard is losing a battle, but because faraway land is receding over horizons you could never have visited anyway. Olber's paradox does something else subtle. It connects your retina to the cosmic timeline. The darkness between stars is the time before stars. The faintness of far galaxies is the stretch of space. The smooth floor of microwave glow is the young universe's last fog lifting. When you look up, you are literally reading a chronicle, not just a postcard. The dark is the unlit chapters. The points are the campfires where the story caught flame. And there's a calming mental move here. It's tempting to think paradoxes demand clever tricks. But the resolution of this one isn't trickery. It's honesty about conditions. The universe expands. Light takes time. Stars are mortal. Put those truths together, and the night falls naturally, beautifully so. So the night is dark for good cosmic reasons. But that darkness carries a related human curiosity. If it's dark everywhere, where is the edge? Is there a center we could point to if only we knew how? If an infinite universe can expand, does it expand from somewhere? Let's take those questions slowly, with toy worlds we can visualize, and then we'll circle back to the real one you live in. Where is the edge of the universe? Where is its center? The cleanest answer is oddly simple. In our best picture, there is no edge and no center in space itself. Not an edge like a cliff where galaxies tumble off, and not a center like a bullseye everyone else is flying away from. The expansion is everywhere, all at once. That sounds slippery until you trade in the right set of examples. Start with the Maples' world, a two-dimensional surface. Picture the surface of a balloon with dots drawn on it. When you inflate the balloon, every dot sees every other dot move away. No single dot can claim the honor of being the center of the expansion on the surface. The center of the balloon is not part of the surface. It's in the higher dimensional space you are not allowed to step into if you're a two-dimensional creature living in the skin. To the dots, there's only the surface, no inside, no outside. Yet, crucially, distances between dots still grow. If you don't like spheres because they curve back on themselves, take a raisin bread dough instead. Dots are raisins. As the dough rises, the separations between raisins increase. Pick any raisin. From its perspective, every other raisin recedes. Is that raisin the center? Sure, for that raisin. So is every other raisin for itself. There is no unique center baked into the loaf. Expansion is a property of the dough, not an arrow drawn from a special point. Now, our real space might be flat on large scales, like an endless table, or it might have a gentle global curvature, like a sphere's surface in 3 dimensions. We don't know the full global topology. What we do know, from precision maps of the CMB and the large-scale web, is that over the patch we can observe, space looks very close to flat and the expansion is uniform. Every sufficiently distant galaxy sees the others recede, and none of them is in a privileged spot. So what about an edge, a boundary beyond which there is nothing? Again, the balloon guide helps. The surface has no edge. March in a straight line and you never fall off. In a truly infinite flat space, there's also no edge. Infinity isn't a border. It's an absence of border. What we do have is an observable edge, a limit to how far light has had time to reach us since the beginning of transparency. That's the surface demarcating everything that has sent us information so far. It's not a wall. It's a horizon. Beyond it, more universe, perhaps infinite, perhaps looping back on itself, continues. People also ask, what is the universe expanding into? The best, if slightly zen, reply, it's not expanding into anything. The distances within space are increasing. The math that tracks those distances, the metric changes with time. You don't need an external container for that anymore than you need a larger room to say, today is later than yesterday. Time grows forward without a bucket to pour into. Space can too, but the balloon does expand into a room. You might push back. True in that analogy, but that's because we used a convenient object living in a higher space to give our brains something to grip. The whole point of the analogy is that the surface doesn't know or need the room. If you live on the surface, your rulers and clocks report all the action happening internally. Angles add up a certain way. Distances scale, geodesics curve. The embedding is for the explicable, not for the explained. Another subtlety, the universe we can see does have a kind of center you. Not because you're cosmically special, but because your past light cone, the set of all events that had time to send you light, forms a sphere centered on your location right now. Move to Andromeda and do the same measurement, and you'll find a sphere centered on that location. Each observer's visible bubble is centered on them by definition. That isn't cosmological privilege. It's how light and time work. If this still feels unsatisfying, flip the question. Ask what would be different if there were an edge or were a center. You'd expect to see gradients in the CMB one side hotter, one cooler beyond what tiny ripples can account for. You'd expect different observers to report radically different expansion behavior. We don't see that. We see isotropy and homogeneity at the grandest scales we can measure. The simplest story that fits is also the most elegant. No edge, no center, just a stage that stretches. And this is part of why the infinite but expanding line from the beginning works. If space is already endless, no edges anywhere, then expanding doesn't mean making more edge. It means that if you pick any two far-flung markers and wait, the distance between them grows. An infinite book can have more space between letters without adding a last page. Infinity doesn't run out. It resets the ruler. Next, Let's address the speed worry that often hides behind these questions. If distant galaxies are receding faster than light, isn't that illegal? Doesn't relativity forbid it? The short answer is crisp and calming. No laws are broken, because nothing is outrunning a being locally. The longer answer is a moving walkway, and it's up next. Einstein's speed limit says no object can move through space faster than light in a local sense. It doesn't say distant distances can't grow so quickly that when you divide distance change by time, the number looks bigger than the speed of light. That distinction sounds fussy until you picture the right scene. Imagine you're on a long airport moving walkway. You can walk at, say, 5 kilometers per hour relative to the belt. The belt itself carries you at 10. Relative to the floor, you're covering ground at 15. If someone far away is on a different walkway moving the other way, the distance between you might grow faster than either of your walking speeds. No one's shoes are smoking. No local speed limits are broken. The background is doing part of the separating. Space works similarly. Locally inside your room, your town, your galaxy physics is the familiar kind. The speed of light is the top speed for any traveler through that patch. But when you compare two far apart galaxies, you're comparing positions across lots of background. That background has stretched. The rate at which the separation grows can exceed light speed without any galaxy blasting through its neighborhood faster than light. It's the walkway space's scale, not the feet, that's doing the extra work. This is also why light from beyond a certain moving distance will never reach us. Imagine a swimmer trying to reach a shore while the river widens everywhere between swimmer and shore faster than the swimmer can advance. Locally, the swimmer churns water at full pace. Globally, the gap still increases. That's what an event horizon in an accelerating universe means. There are swimmers, photons, who started too far away for the current, expansion, to ever let them arrive, no matter how long they swim. You might wonder, if distant galaxies can recede from us faster than light because of expansion, how do we ever see ones that today are beyond that speed? The trick is timing. When the light left matters. Many galaxies you see in deep images emitted the photons during an era when they were closer, in the moving sense, and the expansion was slower. Those photons set off, fought the current, and made it into our boat before the current strengthened. Today, the same galaxy might be beyond the now horizon for new signals, but the old light is already en route like messages in bottles, thrown upstream before the flood. Here's a trio of takeaways you can hold without math. Local physics is local. The rules you trust in labs and kitchens still hold. Atoms don't stretch. Solar systems don't drift apart. The cosmic speed limit applies within neighborhoods. Global comparisons can exceed local limits without cheating. Recession speeds faster than light are bookkeeping of the stretching background, not rockets breaking rules. Horizons are about communication, not existence. Crossing a communication limit doesn't erase a galaxy. It just ends the possibility of receiving new light from it. This often leads to another question. How big is the part we can see? The answer surprises people. Because of the expansion during light's journey, the stuff we can observe today, what's inside our observable universe, isn't a simple age times speed of light sphere. It's much larger in radius, on the order of dozens of billions of light years, because the space between us and the emitting sources grew while their light traveled. Meanwhile, the universe may be vastly larger still, perhaps infinite. The observable bubble is your now accessible neighborhood, not the whole city. None of this means we're cut off from meaning. Horizon talk can sound lonely. But remember, the universe has already sent us plenty. The CMB carries a message from near the beginning of transparency. Galaxy surveys map the web in 3D out to billions of light years. Supernova, gravitational lensing, the faint ripples in the CMB's temperature and polarization, they're a choir. The acceleration story, the flatness story, the dark matter story. They're not hunches. They're converging readings from different instruments tuned to different verses, which is a good cue for our next pause. How do we actually know all this? If we've set aside equations and spared you the jargon, what's the evidence you can hold in your hand like a smooth stone? Let's lay out the ladder, step by step, and see how each rung keeps you safe. We build our picture of the expanding, possibly infinite universe, the way you build trust in a bridge, not by admiring the paint, but by checking the independent supports. No single measurement carries the whole weight. The strength is in the cross-checks. Start at home. We measure distances to nearby stars, using parallax, the tiny apparent shift in a star's position as Earth orbits the Sun. It's celestial triangulation, and it gives us a baseline. From there, we identify standard candles objects whose intrinsic brightness we can know, for example, certain kinds of variable stars. If you know how bright something truly is, and you observe how bright it appears, you can infer its distance. That's the first stretch of the cosmic distance ladder. Farther out, those special type Ia supernova exploding stars with remarkably uniform peak brightness become our beacons. In the 1990s, teams collected many of them across deep distances. Plot how faint they are, a proxy for distance, against how red-shifted they are, how much their light has been stretched, and you get a history of expansion. The surprise was in the trend. The distant ones looked too faint. The universe had expanded more during their light's flight than a simple coasting model predicted. That was the first clean, jaw-dropping hint of accelerating expansion. But we don't rest the case on that. We also listen to the cosmic microwave background. Its speckle pattern isn't random. The size and spacing of hot and cold spots encode the geometry and contents of the universe. A typical angular size of a certain pattern in the CMB acts like a yardstick. Measure how big that yard looks on the sky, and you learn about the curvature of space and the expansion history since. The CMB says, nearly flat stage, and points to dark matter and dark energy in specific proportions. We then check the large-scale structure, how galaxies cluster across vast distances. A subtle ripple, a preferred separation scale, the fossil of sound waves in the early plasma appears in galaxy maps as well. Those baryon acoustic oscillations give us another standard ruler at later times. Again, measure its apparent size across redshifts, and you trace expansion independently of supernova. The result agrees. Acceleration. We watch gravitational lensing, where massive foreground structures warp the paths of background light. The statistics of these distortions tell us how much matter dark and visible has clumped, and how fast that clumping has progressed. That clumping rate depends on the tug-of-war between gravity and the push of dark energy. The lensing story lines up with the others. A cosmos where dark matter built scaffolding early, and dark energy later dampened growth on the largest scales. We also see time dilation in distant supernova. Light curves, their brightening and fading stretched in time, exactly as much as their light is stretched in color. That's a quiet, direct sign of expansion's imprint on time, not just on wavelength. And there's the oldest workhorse, the redshift distance relation itself, first mapped in the early 20th century. On average, the farther a galaxy is, the more its light is shifted toward the red. That's not because the galaxy moved through space so fast. It's because the space between has grown. The relation isn't a straight line across all times, because the expansion rate has changed. Teasing out the change is exactly what the candles, rulers, and ripples do together. You'll sometimes hear about tensions, small discrepancies between numbers inferred from different methods. That's science working, not failing. Each measure has its own systematics. Instruments improve. Catalogs grow. Methods get refined. The broad picture has held through decades of upgrades. A universe that expanded from a hotter, denser state. That is nearly flat on large scales. That formed structure in a dark matter scaffolding. And that now accelerates under something like a cosmological constant. It's worth pausing on how human this is. We didn't pick a story and go hunting for friendly facts. We built instruments that could have told us we were wrong. We asked the same question multiple ways, and when the answers matched, we let the picture stand with caveats where it should, curiosity where it must. That's why phrases like dark matter and dark energy remain placeholders. We're not pretending understanding we don't have. We're naming effects we measure and leaving the deeper, what is it made of, to the next set of clever minds, maybe yours or your grandchild's. So the bridge holds. You can walk out on it at night and feel it hum beneath your feet. Which brings us to a gentler question we promised. What does any of this mean for you? Your day? Your breath? Your sleep? Does knowing that an infinite stage can stretch change how breakfast tastes? Maybe not, but it can shift how you hold ordinary moments. Let's anchor the cosmic in the personal, and let your thoughts settle. Here's the quiet magic. Cosmology is a scale lesson that loops back to daily life. The same picture that gives you horizons and infinities also hands you reasons to exhale. First, the headline that started all this in infinite universe can expand isn't a riddle to wring you out. It's a vocabulary shift. Infinite means no edges. Expand means the ruler spacing grows. Those can both be true. You don't need an outside to grow into. You don't need a center to flee. That's not a loophole. It's the way distance works when the stage itself is dynamic. Second, local life is sovereign. Atoms don't drift apart. Your coffee doesn't stretch thin. Your city doesn't expand because the cosmos does. The forces that matter to you here, electromagnetism in your molecules, gravity in your solar system, are strong, and they bind. Expansion is a background trend that shows up only across gulfs vaster than imagination. Knowing that helps resize worry. The universe can do its slow zoom without tugging your morning into strangeness. Third, the dark night is a feature, not a failure. If the sky were blazing in every direction, sleep would be a myth and astronomy would be impossible. The darkness is a kindness from time and expansion. It leaves room for stars to matter singular, particular, story-bearing. It leaves room for the faintest afterglow to whisper across the ages, so softly that only patient instruments can hear it. Fourth, there is no center to be far from. That's philosophically freeing. You're not exiled to a corner of creation. Every observer can call their point here without stealing that word from anyone else. It kills the anxiety that we're on the edge of something important. There is no edge. The important is what you make inside your bound island. Fifth, endings are slow and local. A far future freeze is not a calendar appointment. It's a trajectory written in pencil, stretched over times longer than the age of everything you've ever known by factors that break language. Your life, your lineage, your planet's long arc, all of it unfolds inside a universe that gives you time and stability on the scales that matter to living things. And sixth, you are soaked right now in ancient light. The CMB photons passing through you as you lie, they started their trip before any star we see existed. That's not romantic frosting. It's literal. Every radio antenna that ever hissed with static heard a bit of it. The universe didn't leave us in the dark without a note. It left a receipt. If you want a pocket summary to keep, no edges, no center. Expansion is everywhere, not away from someplace special. Distances, not objects, outrun light. Local physics keeps its promises. Horizons are about messages, not existence. Structure grows where glue wins. Galaxies, stars, and you live on bound islands that ignore the big stretch. Dark matter builds. Dark energy paces. One shaped the web. The other sets the long zoom. Evidence is layered. Supernova, the CMB, galaxy maps, lensing different eyes seeing the same landscape. Now, set the cosmic aside for a breath. and look around the small room you're in. A glass of water, a book, a phone cooling on a charger. Every bit of it is made of atoms forged in ancient stars that collapsed, exploded, mixed, and were reassembled into these quiet shapes. The expansion didn't tear those stories apart. It gave them room. The infinite didn't make the intimate small. It made it possible. If the mind starts to float again, but what if there's something beyond all this? Let it. Curiosity is the exact muscle that built this map. Just remember, you don't have to finish the map tonight. The questions will wait. The sky isn't going anywhere quickly, and neither are you right now, tucked into gravity's firm little harbor, with breath and pulse and a whole history humming in the walls. We'll keep going if you'd like. There are 5 blocks left. We can visit horizon illusions, the difference between nothing and something in physics speak, or how cosmology sneaks into GPS and calendar time. Or we can stop here with enough to hold. An infinite stage that can stretch, a night that is dark for good reasons, and a life that's still your own, lived at the only scale where meaning is made. Close your eyes if they're heavy. The universe will keep on expanding patiently, everywhere, into nothing at all, and it will not mind if you drift. Let's sit with horizons a little longer, because they're the part of cosmology that most messes with common sense, and they're also the reason bedtime sky-gazing is so quietly profound. When we say observable universe, we're talking about everything that has had time to send us light since the cosmos became transparent to light. That makes an invisible bubble around us, centered on here and now. It isn't a wall. It's a limit set by age and speed. If a lighthouse switched on too late, or was too far when it did, its beam just hasn't arrived yet. Think of news traveling over old telegraph wires. No matter how many messages are out there, you can only read the ones that have reached your desk. There are 2 especially useful horizons to keep straight. The look-back horizon, how far we can see into the past. When you look at a very distant galaxy, you're seeing it as it was billions of years ago. That's why deep images are time machines. They show toddlers when today those galaxies are adults or maybe gone. The event horizon, which is about communication. Because the expansion of space is speeding up, there are places so far that even light leaving them today will never reach us. Not in any future. It's a boundary between can never hear from and will never hear from. And it grows more decisive as acceleration continues. Here's a picture that helps. Imagine you're in a boat in a very broad river that's widening everywhere. Nearby swimmers can reach you. Strong ones farther away might still make it. But beyond a certain distance, the river widens faster than any swimmer can cross. They can signal, splash, try their best, and the current will still carry them away faster than they can overcome. That cutoff is like our event horizon. It doesn't say there aren't swimmers out there. It says their new splashes can't ever reach your hull. This is where a common confusion sneaks in. People hear, the universe is 13.8 billion years old, and think the edge of what we can see must be 13.8 billion light years away. If space weren't expanding while light traveled, that would be a decent guess. But space did expand by a lot during the light's long journey. So the farthest stuff we can now observe is much farther away today than age times speed of light. It's like watching a friend walk toward you on an escalator that's moving away. You can see them because they started close enough long ago, and yet the distance between you now is bigger than you'd think because the ground stretched while they walked. Another horizon subtlety. Horizons are personal. An observer in a distant galaxy has their own bubble, centered on them, with a different set of objects inside. Neither bubble is more real. Each is the natural consequence of light's finite speed and the shared cosmic clock. That's not egocentric, it's just how causality draws circles. Does a horizon cut the universe in half? Not at all. It only divides already connected from not yet and maybe never. And even the never side isn't a tragedy. there's a kind of loveliness to it. The part of the universe we can know already contains a staggering inventory. Billions of galaxies, each with billions of stars, clouds, planets, and who knows what kinds of biochemistry. We don't suffer from a shortage of sky. We suffer, if anything, from a shortage of nights to take it in. Now, horizons can play tricks on our intuition. For example, when we point a telescope at a faint smudge and call it a galaxy 13 billion years in the past, it's easy to imagine that galaxy is now sitting exactly where the smudge was, waiting to be photographed again today. If only we had a bigger lens. But remember the river. While that light was crossing, the space between us grew. Where is it now? Is a slippery question, because now for them is not the same as now for us, in any absolute sense. Still, in the everyday language we use, the best answer is farther than the place your eyes are showing you, often much farther. One last horizon to tuck into your pocket. The particle horizon, which is basically how far the farthest messengers have come since the very beginning. It's the ultimate look-back limit. Beyond it, there's more universe we just don't have the post yet. Horizon talk can sound chilly. Walls, nevers. But it's the opposite. Horizons are proof that the universe is big enough and interesting enough that we need careful words to talk about what's within reach, and they're kind. They let us do honest science in a bounded arena, measure what can be measured, infer what can be inferred, and leave the rest to curiosity rather than anxiety. If your mind's tired, that's okay. Let horizon mean this tonight, the quiet line between what your eyes can hold and what they willingly let go. Beyond it, more night. Inside it, more than enough wonder for one human life. Tomorrow, if you like, we can ask what physicists mean when they say nothing, and why the vacuum of space is one of the most something-nothings you'll ever meet. Physicists use the word nothing in ways that make philosophers, and sometimes the rest of us, tilt our heads. Out in space, away from stars and dust and gas, you can have a region that seems empty. No air, no atoms, nothing to touch. That's a good everyday vacuum. But in modern physics, even the best vacuum isn't a pure blank. It's more like a stage with the lights turned low, cables hidden, and the orchestra pit quiet but still there, ready. Here's a friendlier way to say it. The universe is filled with fields. A field is a quantity that has a value everywhere, like temperature on a weather map. You can't hold a field in your hand. It's a way of keeping track of what can happen in each tiny patch of space. Particles, electrons, photons, and all the rest are like ripples or excitations in these fields. When the ripples are calm, you don't see particles. When the field gets excited, you do. Even when there are no particles present, the fields themselves remain, with a bit of irreducible jitter, the way a resting guitar string still hums if the room is noisy enough. So empty space is more like a resting instrument than a deleted track. That restless bass state shows up in real, measurable ways. It affects how atoms behave, how light moves, even how the universe as a whole evolves. It also means that when we say the universe expands, it's not that we're inflating a literal nothing. We're changing the distances within a stage that already has rules baked in. This is part of why imagining the Big Bang as an explosion into emptiness isn't quite right. It's closer to say that space itself was once hot and dense everywhere, then cooled and stretched. No air burst out into a room. The room got bigger. The recipe, those field rules, didn't get replaced. The ingredients, the excitations changed. You might hear about quantum fluctuations and picture little particles popping in and out like fireflies. That's not a bad first image, but the deeper point is simpler. The vacuum is active in a subtle way. Leave a field alone, and it will still contribute quiet background effects. We're not adding woo. We're admitting that nothing in physics isn't a metaphysical abyss. It's the lowest energy condition of something that can carry energy. Then there's curvature, the shape of space-time itself. Even if you remove all matter and radiation from a region, space-time can still be curved by what's elsewhere, or by its own built-in properties. That shape changes how straight lines behave, how time flows, how light travels. So even a matterless patch isn't featureless. It inherits the geometry of the larger whole. Why does this matter in a sleepy documentary? Because it cleans up language that would otherwise tie your brain in knots. When we ask, what is the universe expanding into? We're smuggling in the idea that space is moving into a bigger, emptier container. But if nothing is really no points of space at all, there is no container. The distances that define space are simply getting larger between places that already exist. The outside isn't a reserved seat waiting to be filled. It's not defined. A second reason, it softens the scary parts. People hear vacuum and think fragile, hostile, dead. In practice, the quiet of space is exactly what allows subtle messages, starlight, galaxy light, that ancient microwave glow to cross unimaginable gulfs intact. A crowded universe would be bright and short-lived. A spacious one, with a nothing that's really a calm, well-behaved stage, is a universe that remembers. And a third, it gives us permission to play with ideas like inflation, that early ultra-rapid stretching, without picturing fireworks. In those models, the energy that powered the stretch wasn't gunpowder stuffed into a void. It was energy stored in fields associated with space itself, which then relaxed and handed their energy to the hot soup of particles. No crater, no shrapnel, just a fierce opening crescendo, settling into the long, slow symphony we inhabit. There's a natural follow-up. If the vacuum has an energy, could that be related to the dark energy pushing the expansion to speed up now? Many physicists suspect a connection dark energy might be a kind of vacuum energy, but the numbers don't line up cleanly with our simplest estimates. That mismatch is a neon sign that we still have work to do. The nice part is, the evidence for acceleration doesn't hang on the explanation. We measure the push. We're honest that the why behind it is part of the adventure still unfolding. So tonight, let nothing mean the quiet, sturdy stage. Not a threat, not a void. A canvas stretched just right, so paint stars, planets, oceans, people can stick to it for a while. In a minute, we'll swing back from philosophy to practical questions. People often ask about expansion, the kind that show up in comments, classrooms, and late-night kitchen conversations. Quick, clear answers can keep the wonder while trimming the weeds. Let's do a friendly, myth-busting, round-short questions people actually ask, with plain answers you can carry. Are we at the center of the universe? No center in space. Every faraway galaxy sees other galaxies receding roughly uniformly in every direction. What is centered on you is your observable bubble, the region that's had time to send you light. If you moved to another galaxy, you'd be at the center of that bubble. Center is about what you can see, not about cosmic VIP seating. Was the Big Bang an explosion? Not an explosion in space. An expansion of space. No debris flying into a pre-existing emptiness. All points were once closer. All points then drifted apart. Imagine raisins in rising dough, not a grenade in a room. If space expands, why don't atoms or solar systems expand? Because other forces are stronger locally. Electromagnetism holds atoms tight. Gravity holds solar systems and galaxies together. Expansion only shows itself across regions with no stronger glue. Can galaxies move faster than light? Nothing moves through space faster than light locally. But the distance between very far galaxies can grow faster than light because the background stretches. That doesn't violate relativity. It's like two ants on a rubber band that's being pulled. Neither ant runs super fast. The band adds extra separation. Will the universe tear apart everything in a big rip? With our current best fit dark energy behaving like a steady cosmological constant, no rip. Bound systems remain bound. Space keeps stretching on the largest scales. Your coffee cup survives. Only if dark energy grows stronger with time would dramatic rips loom, and current measurements don't point that way. If space is infinite, does everything that can happen actually happen somewhere? An infinite space with similar physics might repeat patterns. You'd get countless galaxies, stars, histories. But exact copies and grand multiverse claims need more than bigness. They need specific assumptions about randomness and initial conditions. Fun to ponder, not settled. Are Andromeda and the Milky Way really going to collide if everything's flying apart? Yes, because locally gravity wins. Andromeda is close enough that the mutual pull between our galaxies outmuscles the background expansion. In a few billion years, we'll merge into an elliptical Milk-Dromeda. Expansion doesn't forbid local drama. It just sets the large-scale trend. Does expansion affect my life in measurable ways? Not directly. Your body, house, and city are glued by forces that ignore the cosmic stretch. Indirectly, yes, because the expansion history shapes the night sky, the calendar of cosmic events we can observe, and the raw material story of everything around you. Could we surf expansion to go faster than light? In science fiction, you'll see warp bubbles. In real physics, we don't know how to create or control space-time the way that would require, and the energy bookkeeping looks forbidding. For now, the answer is no practical shortcut, and even if one existed, nature usually charges steep interest. What's outside the universe? If by universe you mean all of space and time, then outside doesn't point anywhere. It's like asking what's north of the North Pole. If you mean outside the observable universe, the answer is more of whatever lies beyond our horizon. Maybe more of the same, maybe different global topology. The important bit, outside, isn't a place you can currently go. Why is the night sky dark again? Because stars haven't been shining forever, and because space stretches light. Darkness is time and stretch made visible. What's the fate of everything? With steady dark energy, the universe keeps expanding. Galaxies drift beyond each other's reach, stars burn out, and what's left cools. It's a slow fade, not a sudden end measured in ridiculous timescales that make even geology blush. On human scales, the universe is steady enough to live, love, and learn. Two bonus clarifications that clean up language. Before the Big Bang is murky, because time itself is part of the story. Many models don't have a meaningful before, the way north of the North Pole doesn't have a meaningful location. Some speculative ideas propose earlier phases. If they leave testable fingerprints, we'll go looking. Until then, before is more poetry than physics. Nothing in casual talk means empty of stuff. In physics talk, it usually means the lowest energy state of the fields and geometry. Those aren't the same, and that's okay. Use the version that fits the conversation you're having. If you hold only 3 sentences from this whole myth bust: 1. Expansion is everywhere, not away from a special spot. 2. Local life is bound together and safe from the stretch. 3. Our picture isn't guesswork. It's a tapestry of matching clues. You can let the rest float. If one question keeps tugging at you, that's not a problem to fix. It's a companion. In a moment, we'll wrap the whole journey, the infinite expanding stage, the horizons, the evidence into a single, quiet frame you can take to sleep. Here's your one-frame version, the kind that fits on the inside of your eyelids. The universe does not sit in anything. It is the anything, the network of places and times with rules for how distances, light, and matter behave. At some early moment, everywhere was closer to everywhere else. Since then, the ruler spacing has been growing. That growth doesn't need a border, and it doesn't pick a favorite spot. If space is infinite, it was infinite then and is infinite now, with more room between distant markers today than yesterday. Because light has a top speed and time is finite, every observer lives inside an information bubble, defined by what has had time to arrive. That bubble isn't a fence. It's a gentle truth about cause and effect. Beyond the bubble, the universe continues. Some of it will eventually speak to us. Some of it never will, because the background current is too strong and the swimmers are too far away. None of this changes what exists. It changes who can talk to whom. Inside the bubble, we've read a lot. An ancient afterglow that's the smoothest light in nature. A web of galaxies laced by invisible matter. A faint, steady push that makes the large-scale drift speed up. We didn't assemble that picture by preference. We audited it with different tools that could have disagreed, and very often, they didn't. Nothing about this requires you to feel small. The word infinite can trick the mind into thinking insignificant. But significance isn't a ratio, it's a relation. A note isn't less meaningful because the symphony is long. A breath isn't less real because the atmosphere is vast. The hugeness around you is the context that lets tiny things endure without being instantly erased. It's not a contest. It's a kindness. And nothing about this requires you to feel hurried. Cosmology tells a slow story. Stars take their time. Galaxies take their time. Even the acceleration we talk about is patient on human clocks. The biggest events you'll ever hear about unfolded over ages longer than the total time humans have had words. You're not late. You're early by any reasonable measure. So, what is this knowledge for? It gives you a posture more than a plan. When you look at the night and feel the tug to understand, you can relax into a picture that is both coherent and welcoming. No edge to fear falling from. No center to fear being far from. No secret wind blowing the atoms out of your hands. A stage that stretches slowly while bound islands, galaxies, stars, lives carry on their intricate work. It also gives you a way to hold mystery without panic. The words dark matter and dark energy aren't admissions of defeat. They're honest labels for pieces of the puzzle we've mapped by their effects and haven't yet touched by the handle. That's not a flaw. That's oxygen for the generations ahead. The map is detailed enough to trust and open enough to invite. If you want a closing mantra for nights when thoughts race, the universe can be infinite and still expand. Expansion is distance growing, not stuff speeding. Horizons are about messages, not walls. My life happens in the local, where bonds are strong. The evidence is layered. The unknowns are honest. Say it once, and let the words soften. Let them become shapes rather than syllables, like constellations you recognize even if you forget the stories attached. And before we close, a small gratitude exercise that fits the theme. Pick one ordinary thing within arm's reach, a pillow, a mug, a plant. Remember that its atoms were forged in stars that lived and died before the sun existed. Remember that the space between those atoms is held firm by laws that are the same in the Andromeda galaxy as in your room. Remember that the night outside is dark, not because the universe is empty, but because its history and its stretch have conspired to make a canvas you can paint with a few bright points. That's all the epic you need on a Tuesday. When you're ready, let your eyes close. If they pop open again, that's fine. The universe is not grading you on how quickly you fall asleep. It will keep doing its slow, silent work, whether you drift in 5 breaths or 50. We'll end with a handful of gentle what-ifs, and then you can choose to stay or to go under. What if infinite just means no fences, and expanding just means a little more room between friends? What if horizons are invitations to be present, not reasons to feel fenced in? What if your curiosity is the exact size it needs to be for your life? No more, no less. Hold one of those like a pebble on your tongue. Taste it, then set it down. Let's land the plane. You began with a question that sounds like a paradox. How can the universe expand if it's already infinite? The untying is gentle once the language is right. Infinity is about edges or the lack of them. Expansion is about distances. They don't cancel each other. They coexist. An infinite book can have more space between the letters on every page without needing to add a last page. That's the whole trick. From that, the rest followed. No special center, no outside to expand into, no need for atoms to be tugged apart, no violation of the speed of light when faraway galaxies recede faster than any rocket could fly. Only horizons that tell you what can reach you, and when. We peeked at the evidence, not as a data dump, but as a set of voices that harmonize, supernova dimmed by distance and time stretch. The cosmic afterglow whispering geometry and contents, ripples fossilized in how galaxies cluster, light bent by mass in ways that sketch the invisible scaffolding. Different tools, same song. We let the dark night be an answer instead of a problem. We turned nothing from a scary emptiness into a stage at rest. We ended up with a picture that's big enough to carry awe and simple enough to say out loud. You do not need equations to sleep under it. You need a few phrases placed in the right order and permission to let the rest wash past. If you want one last pocket story for yourself or for someone you love, here it is. Once there was a stage with no walls, only rules. It stretched slowly, making room. Light stars rose and fell on that stage, and each light made new dust, and the dust learned tricks. One of the tricks was to become eyes that could look back at the stage and notice both the lights and the room between them. The eyes asked, "Where's the edge? Where's the center?" And the stage answered, "You won't trip. There isn't one. You won't be left out. Every place is a here." The eyes asked, "What about the dark?" And the stage answered, "That's history and kindness. It lets the bright things matter." The eyes asked, "What am I supposed to do?" And the stage answered, "Live on your island. Keep your promises. Let curiosity be your lantern. I'll handle the stretching." That's as good a bedtime story as any of the old myths. And it has the advantage of being how the world seems to work when we listen with careful instruments and honest math. If, as you drift, stray worries return climate, work, family, the small hard edges of real life, know this. None of the cosmic facts erase the local duties. They support them. You are part of the chain that learned to read the sky. That chain survives not by mastering infinity, but by tending rooms, gardens, minds, and relationships at human scale. The universe will expand whether or not you answer that email. The email needs you. That's the scale that chooses you back. So here is your last breath pattern for the night, tied to the story we told. Inhale, no edges. Exhale, more room. Inhale, local bonds. Exhale, I'm safe. Inhale, I can wonder. Exhale, I can rest. Repeat it a couple of times, quietly. Let the words fade until they're just rhythm. Let rhythm become nothing but air moving in and out. Let air become sleep. And if you don't sleep, if your brain rides the moving walkway for a while, no penalty. You've walked through a big idea tonight, kindly. You've learned to hold infinite and expanding in the same palm without squeezing. Tomorrow, you'll still be in a universe that keeps its promises on the scales that matter to you. The stars will still be there, and the black between them will still be the oldest story you can see. Thank you for being here, for asking a question most people never ask, and for staying long enough to hear the soft answers. The stage is stretching. The lights are warm. Your island is strong. Close your eyes when you're ready. Good night.